Look at this figure. A fellow is standing in front of a step, has the height of 2 feet. In our language, we can say that it has the potential V second, and he's standing at the region where the potential is V first. This I am considering as the second region, and this is the first region. Okay, so he can easily climb over the step and walk through this region. In that case, I can say that his energy is greater than the potential V second. Okay, if I increase the height into some 8 feet, so the potential is V second is this much. I'm saying that he's an energetic person, still he can climb over this place by a jump and walk through this region. In that case also I can say that his energy is greater than the potential of that region, second region. Okay, and if I increase the height further into around some 20 feet, so the potential is this much. I'm saying that he's not able to climb over this place. Okay, in that case, if he moves in this direction, he can hit this wall and he can come back. So this point I am saying that this is a classical turning point, and in this region, this is the second region. And if I increase the height further into infinity, still he is not able to enter this region. So that region is known as classically not allowed region. Classically not allowed region, where the energy is less than the potential, and this is the region where he can move freely because his energy is greater than the potential of that first region. So this is classically allowed region. Okay, so there is a classical turning point which demarcates the boundary between classically allowed region and classically not allowed region. And this is a two-dimensional situation. I am explaining a two-dimensional situation, and I am contracting this situation into a one-dimensional situation for a particle, that particle is not able to enter the region where x greater than x naught has the potential greater than the energy of that particle. Okay, so the particle classically cannot enter into this region where x greater than x naught, and it's allowed to move in the region if x less than x naught. Okay, where the energy is greater than the potential. Okay, but in quantum mechanical perception, there is a finite probability of finding the particle in the second region. If there is a finite probability of finding the particle in the second region, there is a necessity for the wave function to be continue beyond this region, beyond the classical turning point. For that, the wave functions and its derivatives have to satisfy some conditions, and that conditions are known as boundary conditions, which we are going to discuss now. Okay. The time independent Schrodinger equation is, as we know, minus h bar square over 2m d square u by dx square plus v of x u of x equal to e into u of x, where u of x is our wave function. And let me put it as equation 1. And d square u by dx square can be represented as u double dash of x, and that is equal to, from this equation, we will get minus 2m over h bar square e minus v of x into u of x, e of x into u of x. Okay, x into u of x, and let me put it as equation 2. We know the interpretation of mod u of x square as the probability density, and integral a to b mod u of x square dx as the probability of finding the particle in an interval a less than or equal to x less than or equal to b. Okay, this requires that our wave function u of x be finite, continuous and single valued in the interval minus infinity to plus infinity. Okay, and these conditions are known as admissibility conditions. In the case of two regions 1 and 2 separated by a classical turning point at x naught, this conditions means that u1 of x0 should be equal to u2 of x0, where u1 is the wave function in the first region and u2 is the wave function in the second region. So the wave function in the first region at x0 should be equal to the wave function in the second region at x0. Okay, and let me explain this admissibility conditions more. For example, I am considering a wave function like this. I'm considering a wave function u of x like this. This is the point x0, wave function like this. Okay. Actually, this wave function is not continuous. We can check the continuity by using this equation. Left hand limit should be, for a continuous wave function, left hand limit should be equal to right hand limit, and that is equal to f of x0. Okay, so if f of x0, and if our wave function is like this, at a point x0, u of x has two values. Okay, u of x has two values. This is u1 of x0 and this is u2 of x0. Okay, at a position, wave function has two values. So wave function, the u1 of x0, u2 of x0 we know. So we can find out the probability of finding the particle. Probability of finding the particle is u of x0, u of x square. Okay, probability, general equation is probability of finding the particle is mod u of x square, mod u of x square. Okay, so this graph tells us the probability of finding the particle at a position has multiple values. The probability can never be multiple values. Probability can have single value, can have only one value at a position. So this wave function is not admissible. Okay, so this wave function is not admissible because this is not a continuous wave function. So we can check the continuity like this. Left hand limit should be equal to right hand limit should be equal to f of x0, or limit h tends to 0, f of x0 minus h should be equal to f of x0 plus h should be equal to f of x0. Okay, limit h tends here also limit h tends to 0. Okay, limit h tends to 0, f of x0 minus h means when we are approaching from left hand side, at x0 we should get one value, and that should be equal to the value which we get when we are approaching from the right side. Okay, but in this graph, when we are approaching from left side, we get one value u2 of x, and when we are approaching from right side, we will get another value u1 of x0. So this graph is not continuous. If the graph is not continuous, then this will not satisfy the admissibility condition. So we can say that this is not an admissible wave function. Okay, and so this has two values at a point. This is multi-value. This has two values at a point. So the wave function has two values at a point will not be admissible, and if it's not continuous, this will not be admissible. Okay, and let me check another wave function. U of x. This is x, and if the wave function is like this. Okay, this is a continuous wave function, but at the point x0, this has two values. Okay, our wave function has two values at a point x0. So that wave function is also not single valued. That wave function is also not admissible. And let me consider another example. This is x and this is u of x. Okay, so I'm considering another wave function like this. At a point x0, this has the value infinity, or at a point x0, this is infinity. That is also not admissible because when we are finding the probability at the point u of x naught, the u of x naught whole square we should find, and that is equal to infinity. So we should not get the probability as infinity, because we know the maximum probability is 1 and the minimum probability is 0. So when we are getting the probability as infinity, that wave function is also not admissible wave function. Okay, so the admissibility conditions are: the wave function should be finite, wave function should be continuous, wave function should be single valued. That means u at boundary. Okay, so u1 of x naught should be equal to u2 of x naught. We have already gone through the conditions of wave function u of x. U of x is finite and continuous everywhere. The conditions of the derivatives of u of x, that is u dash of x and u double dash of x, follows from the Schrodinger equation. And we know the Schrodinger equation is this one: u double dash of x equal to minus 2m over h bar square e minus b of x into u of x. Okay, so the conditions of u double dash of x as well as u dash of x depends on the nature of the potential v of x. Okay, so depending on the nature of the potential v of x, we have three cases. First one is v of x is finite and continuous everywhere, and v of x is finite and continuous everywhere. And second one is v of x has a finite discontinuity at the point x naught, and the last one is v of x has infinite discontinuity at the point x naught. Let's examine one by one. First one is v of x is finite and continuous everywhere. Okay, if v of x is finite and continuous everywhere, and we know u of x is finite and continuous everywhere, so v of x and u of x are finite and continuous. So therefore u double dash of x is also finite and continuous. Okay, and let's examine whether u dash of x is finite at the point x naught. For that, we need to integrate u double dash of x. Integrate u double dash of x from x naught minus epsilon to x naught plus epsilon. Epsilon is greater than 0. And epsilon is an infinitesimal displacement. For instance, let me consider a graph of u double dash of x versus u double dash of x versus u double dash of x versus x. If the graph look like this is the point x naught. Apart an infinitesimal displacement, this is the point x naught plus epsilon, and this is the point x naught minus epsilon. Okay, and this is u double dash of x naught minus epsilon, and this one is u double dash of x naught plus epsilon. Actually, the interpretation of integration by a graph is area under the curve. Area under the curve of a graph is the integration from x naught minus epsilon to x naught plus epsilon. So I need to find the area under this curve. To make it easy, I'm just manipulating this into a rectangle. Okay, by calculating the average of these two values, is u double dash of x naught minus epsilon plus u double dash of x naught plus epsilon divided by 2 is the average value of this two. Okay, so I'm extending this line like this. So I'm going to find the area of this rectangle. that will be approximately equal to area under the curve, because this epsilon is an infinitesimally small distance or displacement. Okay, this is 2 epsilon. So I need to find out the area of this rectangle. That will be equal to breadth into length of this rectangle, and we know the length of this rectangle or height of this rectangle is u double dash of x naught minus epsilon plus u double dash of x naught plus epsilon divided by 2. Okay, so in the RHS this is approximately equal to u double dash of x naught plus epsilon plus u double dash of x naught minus epsilon divided by 2 into 2 epsilon. Okay, and we know a basic relation or basic standard equation of integration, that is integral a to b f dash of x dx is equal to f of x from a to b, and this is also equal to f of b minus f of a. Okay, in that way I can write the LHS of this equation, that is u dash of x naught plus epsilon minus u dash of x naught minus epsilon equal to RHS of this equation is u double dash of x naught plus epsilon plus u double dash of x naught minus epsilon into epsilon. This 2 and 2 will get cancelled. Okay, this is approximately equal to, and I told this is an infinitesimal displacement. Epsilon is an infinitesimal displacement. If epsilon tends to 0, the RHS of this equation is approximately equal to 0. That means u dash of x naught plus epsilon minus u dash of x naught minus epsilon equal to 0. That implies u dash of x naught plus epsilon equal to u dash of x naught minus epsilon. Okay, look at this figure. U dash of x naught plus epsilon is the wave function at this point x naught plus epsilon, and u dash of x naught minus epsilon is the wave function at this point x naught minus epsilon. Both are equal. That means this wave function, the first derivative of the wave function, is continuous at x naught. So u dash of x is continuous at x naught. And case 2 is v of x has finite discontinuity at x equal to x naught. So u double dash of x also has a finite discontinuity at x equal to x naught. This is actually minus 2m over h bar square. Okay, so let's find out what about u dash of x. U dash of x naught plus epsilon u dash of x naught plus epsilon minus u dash of x naught minus epsilon is equal to integral x naught minus epsilon to x naught plus epsilon u double dash of x dx. Okay, look at this figure. This is the potential v of x versus x, and here we are considering the case v of x as a finite discontinuity at x naught, x equal to x naught. So look at this. In this figure, v of x has a finite discontinuity at x equal to x naught. Okay, in this region the potential is v first, and in the second region the potential is v second. Let v first equal to v of x naught minus epsilon. This is the point x naught minus epsilon, and this is the that is in first region, has the potential v first, and this is the point x naught plus epsilon. In the second region has the potential v second. So v first equal to v of x naught minus epsilon, and v second equal to v at x naught plus epsilon. Okay, so here this is equal to we can substitute this value for u double dash of x. We will get minus 2m over h bar square e integral x naught minus epsilon to x naught plus epsilon u of x plus 2m over h bar square. V of x is v first from x naught minus infinity, x naught minus epsilon to x naught, and u of x dx plus 2m over h bar square. V second is the potential from x naught to x naught plus epsilon u of x dx, and this is equal to minus 2me over h bar square. So this is the integral x naught minus epsilon to x naught plus epsilon u of x dx. Okay, so that means we have to find out the area under the graph of u of x versus x. So area under the graph, as early we can find u of x naught minus epsilon plus u of x naught plus epsilon over 2 into 2 epsilon. This is the length into this is the length into breadth. Okay, 2 epsilon plus 2 mv first over h bar square. Again, the area is u of x naught minus epsilon plus u of x naught over 2 into the breadth is epsilon. Okay, epsilon plus 2m into v second over h bar square u of x naught plus u of x naught plus epsilon over 2 into epsilon. Okay, into epsilon, and this is approximately equal to, when epsilon tends to 0, this is approximately equal to 0 because all of these terms contain epsilon. Okay, so RHS of this equation become 0. RHS of this equation becomes 0. That means the first derivative of the wave function is continuous across the boundary. Okay, continuous across the boundary. U dash of x is continuous across the boundary. And this is the case 3. V of x has an infinite discontinuity at x equal to x naught. V of x has an infinite discontinuity at x equal to x naught. This is our Schrodinger equation, and this I can write as u double dash at x naught over u at x naught equal to 2m over h bar square. V at x naught is infinity. V at x naught minus e equal to v at x naught is infinity, so this is equal to infinity. A possible solution for this equation is u at x naught equal to 0 and u double dash at x naught equal to non-zero and finite. Okay, and finite. If u double dash of x naught equal to non-zero and finite, and u of x naught equal to 0, then we will get infinity. Okay, u of x naught equal to 0. since the continuity of u of x requires that, continuity of u of x requires that here u of x not equal to 0, and continuity of u of x requires that u of x equal to 0 for x greater than x naught. Okay, if u of x equal to 0 for x greater than x naught, then u dash of x equal to 0 for x greater than x naught, and u double dash of x equal to 0 for x greater than x naught. And for instance, if our wave function looked like this in one region, this is the point x naught, our u of x, our graph of the u of x will look like this. Okay, if this is x, if x greater than x naught, then u of x equal to 0, as well as u dash of x and u double dash of x equal to 0 for x greater than x naught. And we know how the sinusoidal function looks like. Okay, I'm drawing a sin x, I'm drawing the graph of sin x. This is x and this is sin x. Okay, and we know this is the graph of sin x. And I'm drawing another graph. I'm drawing another graph denoting the slope of this graph at each point. Okay, slope of this graph at each point. Look at this. Here, if I'm finding the slope, I get maximum slope here. Okay, then if I go in this direction, slope will become less, and at this point slope is equal to 0. Okay, so if I'm denoting the slope of each point. Here I'll get the maximum slope, here I'll get the maximum slope, and then gradually the slope is decreasing, here it's 0. Okay, gradually the slope is decreasing, here it's 0, and then the slope increases in opposite direction. Slope increases in opposite direction, and here this will become maximum. Then again the slope is decreasing, in opposite direction, decreasing in this direction, and here the slope is decreasing in this direction, here it's 0, and again it's increasing in opposite direction, so our graph will look like this. Okay, actually we are familiar with this graph. Which graph is this one? This is the graph of cos x. Okay, cos x. How will we get cos x? D by dx of sin x equal to cos x. Okay, when we are differentiating a function, we are getting the slope of that function. So let me consider another example. This is the meaning of differentiation. If I am considering another example, this is x and this is x, and this is, let me consider this u dash of x. Okay, and if this is u dash of x, I'm drawing a graph at the point x naught. U dash of x is finite, infinite. Okay, u dash of x is infinite at the point x naught, and if I am drawing the slope of this function at each point, then I'll get u double dash of x. Okay, u double dash of x, and this is the slope at here. This is minimum, and the slope is increasing, and at x naught slope is infinity. Okay, so this here at this point slope is minimum and then increasing, and slope also becomes infinity at the point x equal to x naught. Okay, so if u dash of x is infinity at the point x naught, then obviously u double dash of x is also infinity at the point x naught. Okay, for u double dash of x be finite at the point x naught, u dash of x must be finite. U dash of x also must be finite at the point x naught. Okay, so u dash uh, u dash of x must be finite, u dash of x must be finite for u double dash of x be finite. And we know here u double dash of x naught is finite, so u dash of x must be finite. Okay, and look at this equations. Here u dash of x is finite, u dash of x naught is finite. Okay, at x naught u double dash is finite, at x naught u dash also must be finite. Here u dash at x naught is finite, but u dash is equal to 0 for x greater than x naught. Okay, and our graph will look like this. If our wave function, if our derivative of wave function is like this, then at x equal to x naught, u dash of x is finite at x equal to x naught, u dash of x equal to 0 for x greater than x naught, so there is a finite discontinuity in u dash of x at x equal to x naught. Thus, we can summarize the boundary conditions of u of x and u dash of x. Okay, u of x and u dash of x. And our first one is u of x is single valued continuous and finite and continuous everywhere, finite and continuous everywhere. And the second boundary condition is u dash of x is finite and continuous, except finite when v of x has an infinite discontinuity, at x equal to x naught. And this is second one. This is third condition. U dash of x has a finite discontinuity, at x equal to x naught when v of x has an infinite discontinuity, the okay.